Welcome back, everyone. I'm John Furrier, host of theCUBE, here in our Palo Alto studios for a special presentation, theCUBE and the NYSE Wired with the GSA Series, where we're covering the future and the current advancements in semiconductors, and of course, powering the AI infrastructure. It's been an explosion. This next panel, got two experts on. The topic is designing to silicon, faster, better, cheaper. As the industry explodes, the boundaries of capabilities is scaling big time, and we're going to unpack it here. The architecture, the verification, how do you get stuff out faster? Everyone wants more faster products, shipped faster. They want the latest revision. We got great guests here. Mamta Bansal, System on Chip, System Design Methodology Automation Engineer at Arm, and Hao Ji, VP of Research and Development at Cadence. Two experts going to break it down in the chips. Thanks for coming on. Good to see you.
Thank you, John. Thank you.
Okay, so I have to ask, System on Chip, the silicon is where the action is, okay? We all seeing the performance gains are at the lowest level. If you look at all the AI engines, they're hiring engineering teams that weren't your classic chip designer software people. They're like old school software people that are just like, software, but they're getting down to the lowest levels. We pointed that out about 2 years ago, and now you have coding assistants kind of doing all the app layer. There's so much development going on at the chip level. That's classic chips and software, and then now other coding coming in. Mamta, talk about this revolution, because I feel like we're about to, it's going to be a breakthrough in silicon. What's your vision?
It is very interesting, John, you asked this question. When I look at the silicon design process itself, it has two distinct paradigms. One is what we know how to do, and that's where agentic workflows are coming. We know how to automate the steps, become from rule-based to more decision-based, data-driven. That is one aspect. But there's one more unexplored aspect. Silicon design is an NP-hard problem, unsolved problems. It is a multivariate problem. We look forward AI to solve that. So I feel the day we break down the NP-hard problems, it will be immense. And that's hopefully not very far away.
Hao Ji, Cadence, talk about what you do there, and the relationship. I think people should know the relationship to you and your customers. What's the things you're working on?
Yeah, Cadence is EDA, electronic design automation. We are actually a software company, but it's a very specialized software, which is the software only helps the chip to design, to verify the chip would work. So we are I would say, backbone of the chip design semiconductor industry. And so in our company, we also foresee this trend that AI is going to be the next trend. So starting maybe 40 years ago, this industry doesn't exist. The people doing chip design at that time, placing transistors manually. And the entire EDA industry started by automation, by enabling people can do their things faster and more efficiently. And we start with a manual layout, then become an automation layout, to become automated verification to verifying the chip is going to work. And I think AI is going to bring the next level of automation, okay? It's going to help us to design the chip better, faster, and collect a lot of the industry best practices and share with the users. And this is where I think Cadence will go.
Mamta, we were talking before we came on camera about the breakthrough with EDA picking up and scaling, some of the things that have to happen.
Yeah.
What are some of those things?
Wow. So I joined Arm a couple of years ago, and prior to that, I had a decade of experience with Snapdragon. I led the SoC design flow methodology automation for a decade worldwide. Even in just 10 years, the way systems are perceived is different. There are three distinct paradigms. One is on the edge, where the laptop, Snapdragon, smartphone, data center is the next one, and the third one is automotive. I feel that this AI revolution is actually creating the funding for all these three big markets. From a designer point of view, the edge is about cost and power. Data center is about inference, per joules, like how many inferences you can do per joules,
Yeah,
per
it's an energy calculation.
It's an energy calculation.
Bounded by
and
energy.
Automotive is about quality, reliability, safety. So I think when the AI, we are going to have a lot more inference. It is very important that we are using the right components at the right place, highest computing power and highest memory bandwidth. So the memory bandwidth will be on a different die. The computing is on a high performance die. This 3D evolution is funded by the AI revolution.
That's a huge statement. I want to unpack that.
Yes.
We're going to unpack this because this is, I think, a really important conversation for today's market. Because a lot of people that aren't inside the ropes are like, it's a hype cycle. But what you just said is interesting, and I was just talking to a friend about this. If you look at the spend of 4G and 5G build out worldwide, trillions of dollars,
Yeah.
base stations, all kinds of equipment, I mean, across multiple vendors. But so that you say, okay, was that beneficial? Yeah, we got phones. The iPhone came out of that. Thank you very much. You're getting at something that's interesting because the funding for AI, both physical plant, the big large data centers. I mean, Texas, they love their oil.
Yep.
Right? They love their data is the new oil. They're going to have a lot of data centers in Texas. But then you got the edge, right? So, and the use cases, like automotive.
Yes.
No one wants their car to crash if they have an autonomous
Correct.
driver,
Yeah.
right? So high quality, SLA, low latency, data center power energy, okay? We all know that. The question is, it's not general purpose. You got to have intelligence in the
Yes.
software.
Correct.
So 3D IC and what Cadence does seems to be a dependency or a relationship that would help an innovator. Some could be a 23-year-old entry-level engineer, says, hey, I think I can make an improvement here. The old way was talk to the boss, 6 months later, do a proposal. This is the change in the workflows. What's your reaction to that?
So I can probably take an attempt at it. So when we look at the AI data center, the massive dies are about 800, the reticle size, they're very massive. And they can be designed only with intelligence. You really need to be ensuring that computing power, your memory bandwidth, your system modeling has to be very accurate. You are going to do AI workloads and optimization of the mesh, which is connecting these 128 cores, very workload sensitive. And that drives all the innovation towards better system modeling, better silicon modeling, and all the way to verification. So that's where AI is really making a huge impact. On the other side, for the memory bandwidth optimization, same thing.
Yeah.
So at a very high level for an engineer, he has an opportunity to go all the way up to the stack, right from silicon to the systems.
This is a dream scenario for technologists.
Exactly.
Hao Ji, you guys are in the predictive, you guys are doing the modeling. This means that you got to be faster because if someone has a spark, an idea, a breakthrough, I mean, could literally just run the table and do that work. How do you guys fit into making that faster? Can you share some of the things that make that work better?
I think, okay, so since you mentioned about prediction and the shift left, is that where I think a lot of technology, I mean nowadays, is that the system design or the chip design is so complex. There's no way you actually know that what you design is going to come out fine, okay? And you cannot rely on traditional technology, say, oh, let me design it and then just verifying it. It will not work, guarantee it, okay? So it is a trend we are seeing is to move this prediction earlier and earlier in the design, okay? A lot of verification, simulation used to be only done at the last step. Now it's moved to the routing optimization stage, okay? And then even earlier, maybe even to placement stage. And then earlier to when you created the netlist, when you make that design, RTL, you already insert those prediction circuitry there, okay? And that is I'm just talking about the regular chip. And then following what the Mamta just mentioned, that with the 3D IC, you even need a system level of a prediction. You have to say, you do a timing and then power allocation. You actually saying that this is the budget of this chip. so that multiple chiplets together, they are going to fit my target. So that is a prediction getting earlier and earlier in the flow. However, are we ready, say, the prediction going to work out of the box? Probably not. And I think a lot of lesson learned, previous history can be entry point of the data. We can train our models, machine learning, AI, that's a very hot topic. That is going to give us additional insight for something which is a so abstract level and help to us to drive the flow.
So you have to, like Mamta was saying, do the front end work.
Yeah.
So the more you do on the front end,
Yes.
because you have to enable some confidence levels in the AI to do the work,
Exactly.
because it's complex.
Yes.
Yeah. Like other way to say it, left shift has been a very common theme, but risk left shift is a new word.
Explain.
I want to reduce my risk two ways. Earlier in the cycle, faster I can find my risk, the better I can address it. It could be verification, emulation, it could be virtual platform. How can I, risk should be left shift. And from the IP point of view, go as low in the IP hierarchy. If we find the issue at system level, it's much harder to address it. We would like IP to be self-contained and testable, and then we go to subsystem level and system level, and then at the whole rack and data center level. So this risk should be at the lowest level and earliest in the cycle. So that's the left shift and go shift down. So it's a...
Okay, so you do the front end work, it's a shift left with risk management built in, basically.
Correct.
Does that change the engineering paradigm? Because the payback on doing that, we're seeing that in all use cases. I mean, when I do digital events, the more homework I do up front, the AI picks up the content in the network. Same thing with designing here. That's key. Does it change the engineering paradigm? What happens on your end? Does it change the participants, the ecosystem?
It does. In the past, IP was horizontal. We will have IP which is go to multiple applications. The IP is changing in two ways. IP is becoming solution oriented. They want to provide the whole solution about interconnect. How do I connect to the software? You should have models. And on the other side, it is becoming application specific. The IP for Snapdragon or Edge will be different from IP for automotive. So the way to look at it, the IP itself is trying to be ready for this revolution. I need to be ready with all my modeling software as well as go vertical for each application. So I think that the whole ecosystem is evolving.
So the question I had for Cadence was multi-die chiplet complexity. You mentioned the verification with AI. I want to get to the edge question because as the models get better and the chips change, you got multi-die and chiplet. What is Cadence doing on this piece to address that verification for multi-die and chiplet?
Yeah, actually Cadence has this, we call the Integrity 3D-IC platform. It is a single unified cockpit to actually specifically addressing 3D-IC complexity. So the way we look at the 3D-IC challenges, one is because the multiple chip can come from different fabs, different process nodes, the data integrity and complexity is enormous, okay? And actually people scatter around trying to find what is the right set of information when you have so many inputs and things are getting conflicts, how you manage that. So integrity is creating this unified system and platform and driving the data input from the top down so that entire stream of the tools are sharing the consistent information. So that's number one, okay? Number two is that with the 3D-IC packaging, then we are actually essentially, you used to have a system. Could be a PCB much larger, now you are shrinking down to a much 3D dimensional integration of the multiple chips. And that is bringing additional challenges, like new challenges people not pay attention to, which we call the multiphysics. For example, the thermal and the mechanical stress, which never part of a traditional EDA domain. It is a new challenges, a new software we are adding to support that challenges. Yeah. Number three is a scalability, okay? You used to solve, people talk about the 4-chip sign-off with taking days to close the verification. Now you have an entire system. How are you going to solve it? It cannot be, oh, a chip you're solving verification for a couple of days, now you have a system, you have maybe 100 dies integrate together, are you going to take 300 days? It cannot be, right? So then how you tackle the problem of the integration and the verification with a hierarchical, massive parallel distributed system, distributed tools to tackle this problem, that's the third challenge that we are addressing as well.
Yeah. On the Arm side, I mean, well known for the low power, high performance and devices, and now data center. You've been there, been a big fan of Arm, as everyone knows. We've covered that. The edge is one of the hot areas I'm looking at. Our team on theCUBE Research is looking at. And inference is the hottest thing. Inference at the edge. You still got to go talk to the training, and then this reinforced learning, retraining. The edge doesn't have training as far as I can tell right now because of the capabilities. And the answer is, well, just put the models where the edge, well, the models are being trained back there. It's like, you want the smartest intelligence at the edge where the new data is coming in. And decisions are being made.
Yeah.
Retail, every vertical. If you're going to take the vision, which I like, which I think is going to be standard, do the homework up front, then let the system do its job. That's decision making. That's where superintelligence, road to superintelligence is achieved. That's everything. Retail, hey, you can have instant things happen before you benefit. What is the edge situation? Because, is there training at the edge today or not? Or when will it get there?
Okay, beautiful. So I think first thing is that ARM CPU is everywhere. Making the CPU AI aware is the first basic step. So the ARM with the V9 architecture has released the SMEs, which is the simultaneous matrix extensions. So you will have a small NPU sitting next to the ARM CPU. You do not have to go back to the main NPU or the GPU. You can do a lot of matrix extension, all that workload, right in the CPU. On the training side, I think this is still a long way to go. But on the edge, like everything will be AI aware. And for that CPU to become SME aware is the key.
You know, language is everything in this world.
Yeah.
I was talking to someone, this is about 8 years ago. There's a difference between the word highly available and high availability. So when you start to get into like what happens, is that available or is it like highly available? And I think what you're getting at here is that the future is you got to have that device support.
Yes.
This is where the model to the edge will work to support, say, hey, I walked into a location.
Yes.
Maybe it's on Wi-Fi or 5G. It can go back, not have a big latency concern, and say, he's in this retail outlet.
Yeah.
And then a model could load.
Correct.
That's where we're going.
Exactly,
right?
exactly. ARM is doing subsystems now. So we were doing only CPUs and then NPUs. There's a lot of interest because why spend time in something which is common? We have a mesh which connects all these CPUs. We provide the software around it. We connect it to the rest of the subsystem. So the inference and training both will become more available to all the product engineers. That is the key. That's how we move to the next level and let people innovate on top of it.
You mentioned product engineers. This is a good topic because if you think about it, Hao Ji, the innovation is going to come from the one that's going to say, why don't we do that differently?
Yeah.
And so if we have the enablement, how does that product engineer let's unpack that. What do you guys see as the scenarios or a best practice today that can be a trajectory into that?
Yeah, I can take, go ahead, take that.
Yeah, so.
Feel free, whoever wants to come.
What we see is that, definitely, especially as a backbone, like I said, the software supporting the semiconductor industry, is what we see is that how we can incorporate the challenges in our offering, okay? And how are we going to free up the resources, the humans, to free them up from the repetition work, routine work, so that they have more bandwidth, more resources to work on the breakthroughs, creativities, and innovations. So we trying to incorporate the AI in our software, for example, starting from, let's say, a very basic things like we call the conversational LLM, right? That you allow the user to talk to the software, asking basic questions. Okay, so now you have very senior engineer who already know, they don't need to talk, they know how to use the tool, versus the new engineers who they don't know. They need read the menu, they need to talk to the senior, getting helps. Now they can just talk to the software, getting help right away. So you're bringing the junior people to behave, work as efficient as the
instant IQ points.
Exactly, exactly. And actually in coding, in silicon design, there's a lot of coding. Apart from EDA, there's a lot of coding. The co-pilots are amazing. Actually, you can write 80% of the code out of the box. And you need to trust and verify.
Yeah,
but 20%.
It's better to have someone else write the code. Debugging is a lot easier than writing it.
Exactly. But the quality of the code and the way its modularization has really improved. And you can coach it. We can say, actually, I would like it to be done this way. This algorithm is more suitable for my application. And the co-pilot is able to make that adjustment. It is amazing. Only yesterday we installed the latest version, and everybody's saying, "Yay! It is so amazing."
There's a party happening. Yeah, it's like happy hour. Let's go celebrate.
Everybody's saying, "Wow! Right? Let's get it. Did you get to that?" So it is amazing.
You guys are awesome. I love the conversation because comes up a lot. I want to ask you because I asked the other panels this too. This is not to give career advice. There are many people from elementary school robotics clubs to high school, college, and in the career. This generation is old and new are coming together.
Yep.
It's not like the new beats the old because it's a system. It's horizontal. It's the whole world. What kinds of things do you see as opportunities from a career standpoint to be a silicon engineer, to write code or design systems? Because I think you're right. We are seeing a new paradigm of how things are built. With AI, you got to do the work up front. I think that's a huge insight. And that's what we're seeing in the data. Whoever does that has back-end benefits. There's a lot of headroom. What advice would you give to someone? So it's not obvious saying, hey, I would want to be a silicon engineer. I mean, if you're obviously in physics and you're coding, you see that. But there are career opportunities.
Yes.
Especially with the coding, 80%.
Especially with the coding. I think just, if you think about, we are at the intersection where not one stream is just on its own. If you go to automotive, or crypto is a good example. Crypto brings finance and technology together. Right? Automotive brings automobile engineering and silicon engineering together. Right? Similarly, we can find so many examples.
It's physical AI is happening.
It's physical AI is happening.
Yes.
Correct. Right? So for an engineer, for a student going to college, if they are in data science and doing statistical modeling and they're studying math, I think they can visualize they have to take some courses in whatever interest, bio, medical, physics, pick something so that when you are at the application side in the job, you know that it will be intersection. It's not going to be pure data. It's not going to be pure medicine. And that is a huge fun for students. Right? In the past, we were like either commerce or science.
Yeah, you were mentioning about IP being horizontal. IP is now specialized.
Exactly.
The stack has changed because the applications have domain knowledge.
IP comes with software now.
Yes.
Which was not the case. Only RTL used to come with software, but now PC Express comes with software. It's a huge way. The coding everywhere.
Mamta and Hao Ji, if we were in college together and we said, hey, let's start a company, we graduated.
Yes.
What would we do? What would you recommend that we do? What would you do if you guys were starting a company today, fresh out of PhD program or whatever degree? What would you do? What would you jump into? Just random question.
I can.
Go ahead,
okay, I have a funny idea.
Okay.
So.
Don't give away all the ideas.
No. So, you know the Moore's law in 1965?
Yep.
It came from because it was changing. The world was changing. I think we are at a point we have to do a Moore's law for AI, and that will give ideas for startups. If we can, and we know that AI is power intensive and power is going to be a big deal. So all the startups and innovation towards power kind of make sense. If we measure inference per joule, that should double every year. And the cost per inference should be half every year. If we think about these two equations, what can I do to reduce the cost and get the inference more effective?
It's a scaling mindset. It's to force the exercise.
Yes.
To saying, okay, if that's the inference per joule as the benchmark.
As the benchmark.
At price performance, that'll drive the innovation.
It will drive innovation.
So that's the area. So if we were going to ideate, we'd start there.
Yeah.
And I like your automotive thing too. How would you look at, and automotive fits into life sciences, pharma, so it's similar. Quality matters.
Yeah.
Data center, I like your angle on that. But it's these new markets like automotive, pharma, life sciences, healthcare.
Yeah.
They're all the verticals that were specialized, oil and gas. I mean, all this stuff, financial. I mean, blockchain is a financial infrastructure revolution.
You're right.
It's digital. It's just physical AI.
Yeah.
What's the quality side? How do you view that? How would we tackle that problem?
I think quality starts from all the way from system software all the way to IP. I do think that today the quality systems are very, I would say, specific, and the bugs are in between.
Yeah.
Wherever the handoff is, the probability of having an issue multiplies.
Yeah.
I think we should focus on where the handshakes are happening, and that's what I feel is the open space.
I was talking to someone who had this big debate because I grew up in open systems revolution, saw the proprietary systems game, and the conversation was heterogeneous interoperability was the big story.
Yep.
But now we had a debate, homogeneous versus heterogeneous. Well, of course, heterogeneous, we all believe that. Yeah, but wouldn't you want to have something homogeneous?
Homogeneous,
So
yeah.
there was a threshold, it used to be called a processor. No one really cared what was in it, it ran. It did things. So the balance between homogeneous systems and heterogeneous systems is an interesting concept. Do I care that a car is solely vertically integrated? Well, not if all the parts are single source. So it's a tough question to answer.
Yeah.
Yeah.
Go ahead.
Random thoughts on that one.
Yeah.
I think it's actually a lot of them are iterative, especially when you say that the homogeneous and the heterogeneous, right? That boundary doesn't have to be firm, and there will be iterations to make optimize the solution as a whole overall system.
Yeah, and I think standardization is key. I would bring back CHI interface, AXI interface, lot of work happening with UCIe consortium, lot of work happening on DDR, DDR, PCI Express, all these are going through a massive acceleration in terms of roadmap. And the fact that Arm and several of these ecosystem partners are central to it, they're trying to bring homogeneity in this heterogeneous integration, because that's going to be paramount.
Standards are really important in
Very important
scalable
standards.
markets. And
Yeah.
there's always a de facto before it gets standard,
Yes.
which is just the vote with your software or vote with the industry. Yeah, it's
Right.
certainly exciting. Well, thank you so much for coming on
you.
the segments. It was really exciting. I love silicon. Of course, siliconangle.com is where all the action is. Design to silicon, faster, better, cheaper. I'm John Furrier, theCUBE. Two experts breaking down design, the future of system on chip, but also 3D IC, and all the innovations about to unleash on the devices. Thanks for watching.